So here's the review for chapter 3. I might start by putting this in the calculator, so put the data in, make sure to call the columns names. I called it foot and height. And so if I go to a data statistics page, swipe over there to foot for X and height for that one. So the first question, is this a clear explanatory variable? Because of the way they said it, they said if there's a relationship between foot length and height. So they did not specify that there is a clear explanatory variable. I think we could use logic and say that it makes more sense for the foot length to predict the height than for the height to predict the foot length. But in the question, it wasn't obvious. So sometimes in the question, they kind of make it obvious. They say something like something predicts or something like that, but not the case here. So that's the data. You would then transfer that to here. So you go probably 12, 14, 16, 18, 20. Just say you do that. And you plot those points. Make sure when you do this, you label this, foot length. Sorry, it's sloppy. And that's measured in centimeters, I believe. And then height are measured in centimeters also. So height in centimeters. And looks like that we need to go 150, 145 to 170 or something like that. So 145, 150, 160, 170. Something like that. And you plot those points, 12, 152-ish, right in there, 13, 132, so that's 150, 15, cover 152, 16, 157, 17, 158, 18, 169, and 20, 160-ish. Okay, so it takes a little while to do. Let's go ahead and do our regression in there too as well. So analyze regression, A plus BX. And I like to have the settings there. If you don't already have that, if you go menu, settings, click diagnostics right there, and that will give you the R-squared value, which is nice to see sometimes. So the second question was use your calculator to find the correlation R between. So you can actually let your calculator do that. So if you go to a calculator page, it's going to talk to that page, and you can hit the variable key. And since we just did regression, it should have an R value there, R and R squared. So R, it even tells you if it's positive or negative. You can tell it's going to be positive because of the thing here. So it's 0.76121 is R, the correlation. Explain how this value confirms your, so you could write, I'm not going to write it out, but let's go back to that just so we can see the visual here. So the line goes something like this, right, roughly. So you can see that it's positive, a number, which means the direction is, the association is positive. As the foot length increases, height is increasing. And 0.76 is relatively close to 1, so the points are relatively close to the regression line, and it's relatively strong, or moderately strong, we might say, something like that. Suppose another student with a foot length of 18 and 160. So 18 and 160 would be, that's right about, wow, that's right about on the line. Pretty close. That's 18, 160. So that point's pretty much on the line. So is R going to increase? I'm not sure what they're asking here. Well, R will increase. The R will get a little bit bigger. So it will increase because the residual on that line is very small, if at all. So it's a very small residual there. So you're adding a point with a very small residual, so the R value is going to get larger. It's not an influential point in that it doesn't have a large residual, or its X value very loose. So it may not affect it that much, but it's going to have some effect on it. Okay, let's look at question number 2. Okay, so for this one, this is about counsels couples who are getting divorced. A random sample of 10 of her client couples provided the data for the scatter plot, where X is the number of years of courtship before marriage and Y is the number of years of marriage before divorce. Okay, so I guess, what's the relationship between length of your courtship and how long your marriage lasts in years? It's only 10 people in there, but it does look like a positive association there. Really, I mean, moderately strong maybe. So if you look at this, what is the slope? So you have to find the slope. So I always find the y-intercept first. So this is the y-intercept. It says the word constant next to it, so that's the y-intercept. This one says, and I might ask you to interpret the y-intercept. So definitely know that one, like we did in the quiz. Interpret the slope. So the slope is 2.45. So first identify the slope. It's 2.4559. I'm going to write divided by 1 just so we can see that as x and y. So as the x, this is x, is 1 there. So length of courtship. So every time you have 1 more year of courtship, your marriage lasts. We predict that your marriage will last 2.4559 years longer. It's kind of interesting, right? The longer the courtship, it seems to have 1 year of courtship equates to 2.45 more years of marriage. Maybe we should just have really long courtships, right? And then get married, and then your marriage will last longer or something. It's probably going a little crazy with that. Okay, so explain the quantity S. So S is the standard deviation of the residuals. So you're combining the idea of standard deviation and residuals all in one statement. So this is talking about Y values. So we're talking about it's measured in years. So if you want to think that way, so 2.749 is the typical difference from the predicted number of years that the marriage is going to last, given the length of ownership or courtship, I should say. Let's see what they said for that one. Boy, that's hard to say in words. Let's just kind of scroll down to number 2, the answers for that one. So this one, the actual number of years of marriage before divorce is typically about 2.749 years away from the number of years predicted by the least squares regression line, with X equals number of years of courtship before marriage. So the actual number of years of marriage before divorce is typically about 2.749 years away from the number of years predicted. So that's kind of your error, or your typical average error there for that, or how many years it would be typically. Okay, so it's predict. Make sure to use the word predict. That's probably the word that's forgotten the most often in that definition. Okay, that's hard to write. Okay, so the psychologist is curious about whether having children has an impact on the relationship. Okay, she draws a second scatter plot. It was kind of interesting. What this couples have, children is open circle. So closed circles are no children and open circles are with children. comment on the impact that having children has on the relationship between length of courtship and length of marriage. So there's a couple things to notice here. So if you look at generally the marriages with children tended to last, the length of the marriage was longer generally. I think in most cases, or in many of the cases, that lasted longer. So you might say typically those marriages that have children tended to last a little bit longer. And you might say something like, so if I drew the regression line for the without children and we drew one with children, I'm not sure if that'd be it. Maybe that would be it. It tends to be a little tighter pattern, it looked like, with children. So a little stronger positive relationship. When you have children, it's a stronger positive relationship that you have. The correlation be a little stronger than it was with the no children couples. Okay, we're on to question number 3. The table and scatter plot describe the relationship between latitude and average July temperatures in the 12 largest U.S. cities. So latitude and then average temperature. So they should have some effect here, but maybe not. I don't know. So let's see. That's a lot of different cities that are represented. Detroit, grew up near there. Okay, so the equation of the least squares regression line is that, where y is the predicted July temperature and f is the, again, I prefer to just put the words in there, but that they define each one, which is fine. Predict the average July temperature for Detroit. So we're going to use the line of prediction. It says the predicted y, or July temperature. It's just going to be 106.5. So we're just going to get our calculator out and just type this guy in there. So you type in 106, just plugging in the formula, minus 0.782 times, in this case, Detroit was a latitude of 42. And so we get 73.656. So we think that we'd say it probably in a sentence. We predict that the average July temperature in Detroit would be 73.656 degrees. Again, you want to say that in a sentence, but that's the idea of it. Find the value of the residual for Detroit. So we know the actual value for Detroit was 74, right? So we do actual minus predicted, right? So actual 74 minus the predicted. The residual is positive, so the residual would be 0.344. Interpret the value of the residual. So our prediction for the average July temperature for Detroit was below what the actual temperature was by 0.344 degrees. So this is measured in degrees here. The value of R squared for this data is 0.277. So interpret this value. So 27.7% of the variation in Y, which is average July temperature, can be explained by the least squares regression line given the latitude. Let's just check that one. These are hard ones to do, so let's see what the actual was, what they said. So it appears, let's see, the actual number of years of marriage before divorce is typically about, sorry, wrong question. So C, about 28% or 27.7% of the variability in the average July temperature is accounted for or explained by the least squares regression line with x equals latitude. Okay, and the last question on number 3. Calculate the correlation. So we do know that, let's see, did they give us anything like that? R squared is 0.277. So if you take the square root of 0.277, you get that. And then we can see that this definitely has a negative slope here. So that this is definitely a negative correlation of some kind there. So we think that that R value will be negative 0.526, blah, blah, blah. So you have to, the key is there because so if you just take the square root of R squared, it's not going to tell you if it's positive or negative because R squared is always positive. So you really have to look, okay, is this a negative correlation? Is the slope negative there? And it was, so that's going to make the difference. Okay, wow, a lot of data here. So let's look at this one. Question 4. What's the relationship between the orbital period and the distance from the sun? Below is computer output for all those. Distance from the sun is measured in AUs, astronomical units, and orbital period is measured in Earth days. So all logarithms are natural logarithms with the base of e. So the first one is orbital period versus distance from the sun. So again, y versus x. When you see that versus, it's y versus x here. So orbital period is your y, and it's listed there. You can see it if you have good eyes anyway. Okay, so you can see this looks to have a little bit of a curved pattern there, that original graph for number 1, Roman numeral 1. So when you do a residual plot, you see maybe a curved pattern there also, and so that's not going to be great. So they tried, well, let's take the y value and take the natural log of that one and do nothing to the x value of distance. And so that graph looks kind of curved. The residual plot also looked curved, so that's not great. But when we took the log of both sides, natural log of both sides, x and y, there, the data looks somewhat linear, and the residual plot looks a little bit more scattered. It kind of doesn't really have a pattern there as much, or certainly not a curved pattern. It's better than the other ones anyway, and it does look like maybe the R value might be a little better there as well. So if you can read that, boy, that's really small. Explain why the information provided suggests that model 1 may not be appropriate for describing the relationship. Model 1 is curved, and so it has a non-linear pattern. The residuals have a curved pattern here, and so because of that, we think that a linear model is not a good fit, may not be appropriate. So B, which model does the best job at summarizing the relationship between distance from the sun and orbital? So I would say that this one does because it has more scatter here, and it does look more linear as well here. And if I can see can't see, I was trying to see the R value, but I think the R value might be a little higher there as well. R squared is, I think it's pretty high there. Yeah, 99.9. So R has to be a little bigger than that one. One has an R squared of 88%. So the R value's got to be a little higher there, which is also a good sign. But again, it's mostly about the residual plot there. I would say it's just a good sign to see the R value higher. Given the equation of the model you chose in part A, use the transformed variable. So give the equation. Okay, so we would say, so the orbital period, I'm just kind of abbreviating there, really sloppy, the predicted orbital period equals, it looks like the equation is 5, if I can read that right, 5.92 looks to be that's right there, I'm reading that. If I didn't read it right, that's what I was trying to read, plus 1.49, if I can read that right, times x, which is the distance from the sun, So that would be your equation. It'd be fine to write it that way. Using the model you chose to predict the orbital period of the Earth, which is distance of 1 AU from the sun. So we're going to plug in 1 for distance from the sun. So first we're just going to type this in. So 5.92 plus 1.49 times 1, because 1. So 7.41. So now we have, oh, I forgot something. Just thought of it. Whew. Hope you're watching this. This should be a log of this. Both of these were logs, right? So log of that and log of this. Oh, so I got to do this. Okay, so we're going to retype this in. So times the log of 1. Oh, that makes a difference, right? Because we took the, is it natural log? Natural log. Okay. Sorry about that. So natural log of 1. Oh, that's interesting. So log and natural log of 1. That's actually a property, I think. Okay, so so it ends up being the same thing. So it's 5.92 is that. So now we have an equation. We have we're going to solve this equation. So solve log of x equals 5.92 at comma x, and we get 831764. Let's double check this one. This is number 4. Hope I did everything right there. I messed up at first, so easy to forget that. Okay, so if you plug that in, natural log of 1, you get 5.9208. So then you do, then you solve that. Okay, so we have I know what I do wrong. So again, I'm used to doing regular log, and so we're going to go menu 3.1 natural log of x equals 5.92 comma x. Okay, now we're talking. So again, they did natural log, so I have to do natural log. So keep that in mind. I wrote log. I think that's why I'm messing up, because I wrote log and I should have paid more attention. It was natural log. And so you have to do whatever they say. And so that's 372. So is about 372 days is the Earth's orbital period in Earth days, right? That's measured in Earth days. Okay, let's go back to that and let me fix my thing again. So this should have been, if I was paying attention, that's even written big enough for me to see. That's natural log and natural log. So this should be ln of that, and this should be ln of that. So that should be the equation. Wow, sorry about that. Okay, so let's try. Now we're to multiple choice. Okay, so let's do some multiple choice. Okay, these might be easier. I don't know. We'll see. Okay, so those interpretation ones are really hard sometimes, and the logarithms can get tricky. Okay, so the following scatter plot is data on wine consumption in liters per person per year and death rate from heart attacks. So, oh, that's interesting. So the more liters of wine per person that you drink, it evidently has a negative correlation. So the more liters you drink, the less chance you have of death from heart attacks. Okay, so the scatter plot shows that countries that drink more wine have higher death rates from heart disease. Higher death rates. No, you drink more wine, you have lower, so that's not true. The amount of wine a country drinks is not related. Well, there seems to be a correlation here, so I don't think that's true. Countries that drink more wine have lower death rates from heart disease. That does seem to ring true. Heart disease deaths is the explanatory variable. Well, actually, wine consumption is the explanatory variable. Country is the, no, that's not true. So C is correct. Okay, that's not too bad. That was a little more straightforward. The height in feet and volume in cubic feet of usable lumber of 32 cherry trees are measured by the researcher. Determine whether the usable lumber can be estimated to from the height of a tree. So we use height to measure volume in cubic feet. So it does look to have maybe linear there. If the data 6.65, 70. So we're talking about that point right there. Wow, that one has a large residual. That looks like an outlier there. So if we remove that with the correlation, well, it has a large residual, so R would change. R is going to get stronger, right? It's positive, so it's going to get larger, I guess. So it's going to get closer to 1. So R will be larger. And I don't think R would not change. R would not be smaller. So it's one of these two for sure. Because the x and y coordinates are larger than the mean x and mean y. I'm just guessing there's some point right in there that's mean x, mean y. All the regression lines go through that point. Because the x and y coordinates are larger than the mean x and mean y. I don't know, but that doesn't look right. Okay, it's because the point does not fall in the pattern of the rest of the data. That sounds perfect. That sounds like the best answer. It's definitely way off the pattern, right? So it's not in the pattern, and that's why removing it would make the correlation stronger because the points are now closer to the line in general than they were when that point was there. Okay, this is, lots of questions about R here, correlation. Correlation resistant, that's funny. It's not resistant. Outliers we just talked about an outlier has a huge effect on the correlation. That does seem to ring true. So which one rings true? That one seems to be true. I don't know how you could poke a hole in that one. If R is correlation to x and y, then negative R, no, actually that would be also R. So switching x and y doesn't change R at all. That's good to know. Now, whenever all the data lies perfectly in a straight line, the correlation could be equal to 1 or -1. So that would be true. And so not all of those are true. It had to say -1, it didn't there. Okay, all but one of the following statements contains an error. Which statement could be correct? Again, more about correlation, more fun with correlation. There's a correlation of 0.54 between the position of football player. So football player is like you could be a quarterback or a cornerback or a lineman. They're categorical, so that can't be it because correlation is two quantitative variables. Between gender, again, gender is categorical, so it can't be that. It's got to be two categorical variables. Correlation between the distance traveled is measured in meters per second. Correlation is just a number. It doesn't have a unit, so that can't be it. We have a high correlation between height and age of children. R equals 1.1. That is so silly. We just talked about how R is between 1 and -1, so that's not going to, it's got to be, I read it. Correlation between soil moisture and per acre yield is 0.53. That's plausible. Nothing seems to stand out about that one. That seems wrong. Okay, like most animals, marine crustaceans are not able to digest all the food they eat. Okay, moreover, the percentage of food eaten that is assimilated, that is digested, decreases, the amount of food eaten increases. Okay, so if they eat more, they assimilate less of the food, I guess. That kind of makes sense. It's just going through them, I guess. Okay, so analysis expects the relationship will be described with the power model, transform the data by taking the natural log of both sides. So it does seem somewhat curved here. So I'm concerned about the curve there. So they're going to take the log of both sides. There's a key point if you read this. A residual plot not shown of the natural logs show random scatter about the line. So show random scatter. So right away that tells you that log thing worked for this one, right? Okay, so based upon the analysis of the transformed data, is a power model appropriate? So we took the logs and, hey, did it work or not? Yes, the residual plot based on transformed data shows random scatter. The plot of the residual plot shows random scatter. They said that, so that does seem true. Let me double check that. Based on analysis, is a power model appropriate? No, the scatter plot versus simulation is nonlinear. We know that, but we're talking about the transform data here. So we're talking about transform data. So we're not really talking about that. No, the scatter plot of food does not show random scatter. Well, we're talking about the transform data. R squared value is not at least, it doesn't have to be a certain, so to be a good linear fit or a good linear model, it doesn't have to be strong. It could be moderate, doesn't have to be a high, certain R squared value. Because the slope of the least squares regression line of the transform data is positive, actually that's the y-intercept. So that's not the slope, so that's just a silly answer. Okay. Least square regression analysis of the pulse rate versus weight for 10 mammal species. Okay, so the relationship between log of that and log of those is approximately linear. So like the original data, get a lot of curve to that. That doesn't look good. But when they took the log of both the x and the y there, it looked approximately linear. And then they did some analysis there. And so we have the analysis over here. The average weight of the this thing is 550. So use the information to predict the pulse rate. Okay, so again, we're talking about, so weight was x, so the pulse with the weight, so this is the y value. I just had to think about it. Okay, so pulse rate is the predicted pulse rate is equal to 2.29836 minus the slope of 0.20099 times x, which was the weight. Okay, so we have our equation, and was there any log going on here? There was. Okay, so relationship between log, so log of this and log of the weight there. And this is regular log, not, gotta remind myself. Okay, so let's try this one. So we have, we're gonna plug in there for weight, we're gonna plug in 550. So 2.29836 minus 0.20099 times the log of 550. Get that? And then you say the log of the pulse, which we're going to call x. Oh, well, we got to use the solve again. Solve the log of pulse x, I'm going to call it, equals this number, comma, x. And it solves it, and it's 56, approximately 56 beats per minute, so that would be B. Did that right this time. Paid attention. Of course, I always go towards log. A lot of folks use natural log a little more. Okay, a researcher wishes to study how the average weight of children during their first year of life. He plots the average versus the age in months and decides to fit a least squares regression line to that. Okay, so he computes the following quantities. Well, oh my goodness, we just don't know all this stuff, right? So you really need these two formulas right here. They're in part, if you can see this, part 1 of your formula sheet. Y bar, the average y, equals a plus b times the average x. And then b, which is the slope, is r times s sub y over s sub x. So using those two formulas, you really need those two formulas to plug it in. So we're going to do the b value one first. So b equals r, which is 0.9, times the fraction s sub y, which is 1.2, over s sub x, which is 3.6. I'm just plugging into that equation. So we're going to get our calculator out and type that in. So 0.9 times control divide, so 1.2 divided by 3.6 is 0.3. So b is 0.3. And then we write in that equation. So I think it was y bar, which we think is given to us as 6.6 here, equals a, which we don't know, plus b, which is 0.3, times x bar, which is 6.5. I'm just plugging into those two formulas I mentioned on the formula sheet. I'm just going to use the solve command just because we can. Solve 6.6 equals a plus 0.3 times 6.5, comma a, because we're solving for a in this case, so 4.65 would be our answer there. Is the y-intercept. So wow, that took a little bit of work to get, but using the formula, so you can just plug in and get it, really. Always figure out the slope first and then use the equation to get the other thing you need. We examine the relationship between X, the height of oak trees, and Y, the number of acorns produced in a 5-year period. Calculate the correlation coefficient and the least squares regression line. If you switched variables, that is, X and Y switched, which of the following would be true? Both the correlation and the coefficient. So one thing we know for sure, the correlation is going to stay the same, right? Correlation doesn't change when you switch X and Y. So the correlation coefficient would change. No, that's not true. Would be changed. So this one, those two are gone. Okay. Okay, so then what's going to happen? So let's just take an easy example. Let's just pretend the original line was this. If I switch X and Y, that'd be weird. They're definitely not the same equation. In fact, you solve them, they're going to have different slopes. So the slope is going to change. The regression equation is definitely not the same there. So they change. So, but the regression line would change. So it's got to be C, right? Because those, when you switch X and Y, it's like an inverse. Unless the slope was 1 and the y-intercept was 0, it's going to change. So, which of the following equations, statements about the high leverage points and outliers are true? So an influential point always has a large residual. Sometimes an influential point is a high leverage point, which doesn't necessarily have a large residual. So that's not true always. Outliers are always high leverage points. Well, outliers have large residuals. High leverage points have large or very small X values. So that's not always true. Remove an influential point always caused a marked change in either one of those things or both. That's absolutely true. That's like the definition of an influential point. So 3 is the only thing that is true. Okay, we're to our last question. Which of the following statements about the standard deviation of residuals is true? So it describes the typical vertical distance between an observed data point and the regression line. Yay, that is the definition of it. B, it evaluates whether a linear model, no, that's what a residual plot does, so that's not what that is. It measures the overall precision predictions made by using the regression equation. That actually is the concept behind it. It's kind of, sometimes we call it like average or typical error. So yes, it is what far they are away from those predictions, how good or bad are those predictions. So 1 and 3 would be the thing there. Okay, again, so if you go to your review, you've got all of your answers there. Just scrolling through so you can stop it if you needed to see some of those in more detail. Great. It's kind of a long screencast, but we got through the whole review. Great. Have a good day.